Kepler, Johannes Kepler.
Johannes Kepler.
Johannes Kepler was a German astronomer, mathematician, astrologer, natural philosopher, and writer on music. But the most likely place which you'll probably come across him is the high school physics textbook. Much like all other famous scientists, he decided to make his own trio of laws. These are pretty cool laws. They let us simulate planets and stuff to a pretty good degree of accuracy. So without further ado, Kepler's first law states that each planet moves in an ellipse around the Sun, with the Sun being at one of the two foci of the ellipse. The way you prove that the planets move in an ellipse when orbiting the Sun is by considering the energy in the system, that being the energy and gravitational potential, and then doing a bunch of maths, which I, to be honest, don't really understand. Polar coordinates, I know what they are, but they make no sense. Angular momentum, not that yet. Now we're doing integration. Where are these? But what I do understand is how to find an equation of ellipse, and that's what I spent a physics lesson doing. You know, you can use like a rubber band or something and have 2 points joining up with a pen and draw an ellipse like this. Basically, I just formed some equations from the lengths because I know that they're constant, then did some mathematical stuff to get the radius from a point to the angle. Boom. Yeah? No? Kepler's second law states that a line joining the Sun to a planet will sweep out equal areas in equal times. I have no idea how he found this thing out because he was probably living in a world without anything. So let's have a look at the derivation. Actually, yeah, it's kind of understand it. We get a triangle where dA is the area and dr is a very small change in the arc. And then we write it in vector form, have a differential equation, and then I'm not sure why, but r with a dot on it and r with 2 dots on it are both 0. So the second derivative is also 0, which means that the change in area with the change in time is constant. Didn't understand that? Neither did I. Kepler's third law states that the square of the orbital period of a planet is directly proportional to the cube of its average distance from the Sun, i.e. this thing. We can either look at this complicated sheet thing, or we can look at the high school explanation of it, which uses Newton's laws of gravitation and centripetal force and set them equal to each other. Then we do some circular motion stuff with time periods, smacking that in there, and then we get this thing, which does show that t squared is proportional to r cubed, as everything in that bracket is constant. Now we got the boring stuff out of the way, we can do some programming. I decided to waste a lesson on making slider things, which was definitely working. Then I decided to make it in 3D to make my life much harder. Here's a box in 3D, and then here's a ball. A ball. A sphere? Oh, here we go. And it's disappeared. Okay, so right now we only have a Sun. As you can see, it's pretty lonely, so time to add some planets in. What I basically did was take a circle, turn it into a parametric equation, and calculate the angular velocity from far, which definitely didn't get off Google. So the planets are the same size and they're not moving. Let me just fix that. Okay, I got one planet to move the circle, and whoa, easy there. Let's turn that velocity down a notch. There we go. Let's get some more. There we go. Right now, we can't really tell where the planets are, which orbit is orbiting, so let's make an orbital path. For this, I used a torus, which is a fancy word for donut, and okay, a 5-sided donut. I'll make it thin enough, and then there we go. Now wait, did I just see Pluto there? Now we know from Kepler's first law that everything is elliptical, so I used the equation we got here and used it instead of a circle equation, and the orbits don't match up. It looks cool, but it's kind of wrong. Better, I guess. Yes, I got. Never mind. Okay, I finally got it working. Turns out I divided by 200 somewhere in my code instead of 100. Now I took the effort to make this thing with plane inclination by Googling and just using some kind of matrix thing, which I don't really understand, but it works. Okay, now everything's turning up. Well, and now everything's turning upwards. So I changed some of the colors and it looks nice, and you can tell there's really some kind of inclination on the planets. Then I programmed in some spirograph stuff into it, but it's basically like those children toys where you do stuff with gears and a pen, and it makes a pretty cool pattern. But this, we draw a line between two planets for every constant increase in time, like every month, and then we have some cool ones, like these.